Well, today is the day to put this little amplifier, which I did do some research. It was released in 1987 by ETI, Electronics Today International, onto a PCB. But before we do that, I just want to prove a little point here. That current meter on that power supply is way out. Well, I want to say at least 90 milliamps out. So what I've got sitting there on the desk is I've got a 470 ohm 5 watt resistor going in series with the positive rail to the circuit, and the multimeter is clipped across these two jumper leads, the red and the white one here, the black and the white one here, and currently the meter is sitting on the voltage scale. So I'm just going to turn the power on and the meter goes up, and we're currently looking at 4.5 volt. Ignore the fact that it's minus, that just means the test leads around the wrong way. But we've got 4.5 volt across that 470 ohm resistor. And this is with the amplifier unloaded, and according to the power supply we're at 20 mA. At 25 plus minus volts. So now if we use
ohms, it's not just fun, it's the law.
To calculate that voltage we got across our meter divided by the resistance of that resistor, that'll give us the draw in current. So we've got 4.5 volts divided by the resistance, which is 470. Basic Ohm's law tells us we've got around 9 milliamps of current draw, not 20. Now if I turn the load off and I load the amplifier into a dummy load and then turn the load back on, at the moment the power supply says we're at about 110 mA. The multimeter says we're at 3.3 volts, so we're actually a little bit lower, so that should mean we should also have a lower current draw. So we're now at 3.3 volts divided by 470 ohms. We're looking more at 7 milliamps. That current meter is pretty much useless. Now, just to confirm what the actual current draw is, right, so with the multimeter on the amp scale with the multimeter in series with the positive supply rail, turn the load on, and immediately you can see there is 10 milliamps of current draw there, which equates to what we calculated from the voltage drop of that resistor, which was around 9 mA. So turn the load off, I'll reload the amplifier back into a dummy load, turn the load on. Now the power supply says 130 mA, but our multimeter says 8 mA. And our calculated value of the drop across that resistor was 7 mA. So
ohms, it's not just fun, it's the law.
Does not lie. That thing, however, does. Because I was a little concerned that this amplifier was drawing 120 mA into a dummy load not doing anything. But it's not. It's only drawing 8 mA into a dummy load not doing anything. Anyway, so let's move on to today's topic of this video. Greetings, the Astro 30 here yet again. Now, I was going to make a PCB for this today, but I thought before I do that, what I want to do is I want to finalize this design and make it a little bit better. The original design is okay, but it can be improved. I also noticed there is a limitation with this. Well, not so much the hardware oscilloscope that's connected to the laptop, but the software that is controlling it. Currently I'm in a ×10 probe and I'm getting a nice clean waveform. I'm just going to set my volts per division down to 5 volts just to prove a point. So in ×10 it looks relatively okay. I'm going to change the probe back to ×1. Well, that's odd. And my peak to peak is stuck at 10.1. This means that I believe I was testing that op amp based power amp with this oscilloscope using ×1, and that's the reason why I was getting results like this, is because there seems to be a voltage limit calculation to the software. If I put it back in ×10, all's good with the world again, and you multiply that by 10, I'm getting 39.2 odd volt peak to peak out, so about 44 watts. This has been running at full power before clipping, which is 1.8 volt peak to peak in, for around about 10 minutes, and the output stage is not hot, and neither is my bass, neither are the drivers. So what I want to look at today is current sourcing, or I'm going to add a current source here to the long tail pair, and that consists of two transistors. Now ignore this transistor here for a second. This is our current source transistor that goes to the positive rail. We also have this 100 microfarad capacitor going across this potential divider of two 10K resistors to ground, and so effectively what this capacitor is and this resistor is an RC network, so that's going to provide a delay of bringing the base voltage up of this to 600 millivolt. So that will effectively give you a turn on mute delay sort of function to the front end, probably only like a few milliseconds or so. It wouldn't be that spectacular. However, what the job of this transistor is basically to add current limiting to this transistor. So there are other ways of doing this. You can just use a simple Xeno diode to ground to do the same thing, and I've seen that done plenty of times, but that's basically the function of this transistor, is acting as a current limit to this transistor. So that's the first thing I'm going to do. Is I'm going to build up this little part of the circuit on a separate bit of the breadboard over here. I'm going to connect LEDs in place of this collector, or an LED in place of this collector, emitter connection junctions, to the negative rail via a 10K resistor or something, and we'll just see what that circuit does. I also have its complementary current mirror drawn down below here, featuring two NPN transistors, one just being turned into a diode by bridging the base and collector together. I'm not going to worry too much about the current mirror section of it. I am going to focus my attention on the current source. So we'll look at that first and just see what it does. Okay, so I've built up the little current source circuit. I've used a 470 microfarad 25 volt capacitor there, just so we can see the delay effects a little bit better, because with the 100 micro in there it's too quick. But if we turn the power on, see there is a slow turn on to that LED, not very slow, but slow enough. So I can see that that is actually functioning. So I'd need to then connect that via two resistors, 100 ohm resistors there, back to each of these emitter connections on the input stage here, and we'll have a look at the output waveform. Ignore the fact it's clipping at the moment. That's only because I reduced the voltage, because the 470 microfarads is only a 25 volt cap, and I wasn't going to put a 25 volt cap across a 25 volt supply rail. So I'll re-increase the voltage back to 25 volt in a minute. Okay, so I've broken the 4K7 from the emitters of the input stage to the positive rail and the join between the two. Got two 100 ohm dropper resistors here off of our current source transistor, so it splits it into two, so it's driving each emitter separately. And now turn the power on, it's back up to 25 volt. Whoa, and something just went with smoke. That was awesome. I'm not sure what smoked. It's the seems to be this Sobel network resistor here. I'm going to take that out of circuit for a sec. As we can see, it's functioning, but the Sobel section is not. So yeah, Just seems strange to me. See, this is why breadboard is not a good design tool, because I just moved the position of this wire, this jumper wire, from where it was connected, which was pretty close to that one, and it stopped smoking. But, well, it's not getting hot to the touch anymore. I don't know what the hell happened there, unless the end of that resistor was shorting on something it shouldn't have been, which is all very possible. I might have been shorting the capacitor out, I don't know. Anyway, that's stabilised our output again, so it's not oscillating. So I'll put it back to 1.8 and look for smoke. No smoke, so no, not getting hot now. Okay, so what was the purpose of that? The purpose of that is that we're actually providing a constant current source to our input stage, and what that is an attempt to do is to reduce the overall total harmonic distortion. Most of your total harmonic distortion comes from your input stage. Now, the original circuit was rated and measured at around about 0.06% total harmonic distortion, 1 kilohertz, full output power. I haven't quite figured out how to use the FFT function on my oscilloscope yet to give a valid distortion measurement, and all I see is my fundamental, but I can't really see any of the third or fourth harmonics. I want to remove this bootstrap circuit and put in the constant current source. Considering I've already got the transistors over here to do it with, we just need one extra transistor. So basically what we would do here is we would take our original circuit here, we would add a resistor, and we'd add an extra transistor up to the positive voltage rail. Same polarity, same type, BC556 here. That would be 2K2 roughly. This is basically borrowed from another amplifier front end that does actually work. And then this would go off to our VAS, or our biasing network. So that's all we need to do, is just add in this extra transistor. This resistor just separates, well, this current source from that current source. We connect that to our biasing arrangement, the string of 3 diodes, and then we'll look at the output waveform, see if we can get our Zobel network resistor to start smoking again like it did before. However, before I do that, what is the actual current being applied to the long tail pair now? Well, that's easy to measure if we measure the voltage drop across one of these 100 ohm resistors, and they should be the same. We have got roughly 422 millivolts going across that resistor. So if we use Ohm's law as usual, we can calculate the current by dividing the voltage by the resistance. So we go 0.422 divided by 100 equals roughly 4 milliamps. Yeah, I was looking for somewhere around about 1 milliamp flow through the input stage, 1 milliamp to 2 milliamps roughly. 4 mA is okay, and that will remain constant. It will never ever change, no matter what the input voltage is doing to the input stage there, that is the input signal. It's going to always remain roughly around 4 milliamp. Very, very good. So let's add the extra part, which is add this extra transistor circuit in. There's supposed to be a 100 ohm resistor here between the emitter and the positive. I will draw up the schematic properly before the end of this video so we can actually just compare the changes from the original to the final. And this is basically the first time I've actually designed a power amplifier. I've built plenty of them, played with plenty of them, but this is the first time I've designed one. It's not actually really designing one, it's taking a current design and just modifying it and making it better. But technically it is basically designing a power amplifier, really. Anyway, I'll just get onto this current source, which will connect to our biasing network, and we'll have a look. Okay, I've got the third transistor installed, and I've got rid of the bootstrap capacitor and the 2 resistors that form the potential divider. So for reference here, I've got rid of this entire thing here. Alright, so I have no idea what's going to happen when I turn it on. It could go off with a bang, so let's hope it doesn't. I'm pretty sure everything is wired correctly and nothing is shorting. That's the biggest concern, is something shorting. So we'll turn it on and see what happens. We have an output. It's a little strange on the bottom there. So I might back the amplitude voltage off. Yes, that's a good indication that it's not biased correctly now. So we're getting a little bit of distortion. But at least the constant current source to the output stage is working. But if I touch that base lead wire with my finger and bring it close to a ground, well, it cleaned the signal up there, see? So it's just layout here on the board. I also found that when I disconnected the Zobel resistor, the noise also went away. So, I should say distortion. Now the distortion's back because I moved it. So, see, now it's stable. Strange, yes, but there you go. Now, screensaver. Now, does that increase our input sensitivity at all? Yeah, only by about 100 millivolt extra, so doesn't really help us with power output. I'm just checking these transistors to make sure they're not getting hot, which they're not. So far very good. Now, what's the next change that I want to make? Well, there's two, in fact. I want to change these drivers from the 4.6 and the 5.6 transistor here to BD139 and BD140 respectively, like they should be. As I wanted to do in the previous video, just never got around to it. Which means changing these two transistors just where this jumper wire is sitting across and reversing a couple of leads around just to make the connections correct. So that's the next thing I'm going to do. When I turn the supply on now, I don't get a large spike in voltage output and then it stabilizes. It just comes straight up. So that's gotten rid of the pop. Okay, I've changed the drivers and swapped the base and collector wires around so they're correct for that transistor's pinout. And hopefully, all going well, that it still functions. So that collector should be going to negative, which it is, and that collector should be going to positive, which it is. Okay, so the only thing is that can happen is it can blow its asshole off, but we'll soon find out. Yeah, it works. Got a bit of bottom distortion there. I'll change my time base so we can actually see that little bottom a bit better. Yeah, that's interesting, that is. I'm wondering if that's that Zobel network again. Let me just touch the wire. Or move this one. I think it's to do with... I'll disconnect the Zobel for a sec. It doesn't exactly flatten out all that well. Yeah, okay, so I reckon that would be a biasing issue too. However, it is functioning. Functioning reasonably well. As I've said multiple times, breadboard is not a good medium for making power amplifiers on. Let's just let it be known there. So what is the final change that I want to make before calling quits on this thing? Well, now as crudely drawn as this is, I apologise for that. Basically what we're looking at here is what they often refer to as a rubber diode. I'm not sure where that term came from. But what this is a bias spreader or a VBE multiplier. It applies even bias to both driver output transistors there. One side's connected to our VAS line, the other side's connected to the constant current line. So this is actually put in place of that string of 3 diodes. And I've got a little trim pot here, so you can actually adjust the amount of current that's going to be flowing in the output stage to just trim it up a bit. You can actually just get rid of this pot and put it straight to the VAS line, but that's basically all it is just a transistor with a potential voltage divider there. And that's my alarm. And so basically we put that in place of the string of 3 diodes. There's just one problem. Well, I'm kind of running out of space here. I might have to stick it in here somewhere, just to put it somewhere and have wires going all over the shit. But my biasing diodes are up here, coming off of my VAS up here. So yeah, it's going to be quite all over the place. That probably would be one of the contributing factors to our distortion at the bottom here. It's nice and clean at the top, but distorted at the bottom. But yeah, as I said, that could be just due to wiring. In fact, I can't clean it up by putting my fingers all over things, but everything seems to be functioning. Actually, if I touch the VAS, once the screensaver doesn't do that, if I touch the VAS, oops, yeah, that resistor keeps on coming in contact with that capacitor, shorting it out. It just smoked on me. If I touch the VAS, that does actually clean it up a bit, but it jumps around all over the place. So I've got to be careful of it doing this, because what it's doing is shorting that resistor to ground and smoking like that. So basically that's putting it across the output load. Anyway, moving on to the VBE multiplier. Okay, our rubber diode is in. I've jammed the pot into the socket board here. I've also got a 1 microfarad cap across the collector and emitter junctions. Will it work or will it explode? Well, we're about to find out. Here we go. No, it actually works. Didn't actually clean up our signal much though. Still a little bit hairy on the bottom. Not by much. You can really see it pronounced there. But I can't see any crossover distortion, so that's good. So what I want to do is just carefully rotate this potentiometer and see if it makes a difference to our output stage signal or not, which currently it appears not to be. But it should be making a difference to the current draw in the output stage. So in order to do that, what I'll do is I will disconnect the input, because we need no input signal, and I will connect a resistor in series with the positive rail with a meter measuring the voltage drop across that resistor. So I'll use a 470 ohm 5 watt resistor here, and measure the current and then measure the voltage drop and then play with that pot and see if it makes a difference, which it should in theory. Got the resistor just sort of like hanging out in the breeze there. So I will set the multimeter up. So we're currently on the volt scale, so if I turn the load on we should see a voltage, 5.4 volt, right. So now if I play with the pot, doesn't seem to appear to be having much effect on the overall voltage there, which I would have thought it would have done. However, I could have wired that VBE multiplier up incorrectly, so I'll just double check things here. Technically speaking, that pot should actually be replacing one of these 1K resistors, not having it in series with it. So, because the two 1Ks are already a potential divider. Adding another 1K in, it's making it 2K versus 1K, and it's not really having that much of an effect on the voltage division. So what I need to do is just remove a resistor and then short the other end of this pot back to the, well, in this case, the base connection of that transistor. One sec. Okay, that modification has been made and the pot's sitting roughly in the center. So we'll turn this back on. We've got 5.4 volt there. I'll play with the pot. That's a bit better, albeit it's a little jumpy. So 7 volt, 6.5. So the current should be now increasing through the output stage, which is as expected, and I am rotating it clockwise, except it's not remaining stable in any sense of the term. Yeah, that's nowhere near stable. And that's not... yes, my output's still loaded. Hang on a sec. Okay, without the output loaded now, yeah, it's not remaining very stable at all, is it? That's rather weak. That's rather... yeah, it's just not remaining stable. Not exactly sure why it's not remaining stable. It should be remaining stable, but yeah, if we increase it, we do actually get a larger current draw. In fact, it seems more stable there, which is interesting. Alright, so if we had 24.5 volt across that 470 ohm resistor, okay, so we got 24.5 roughly. We then divide that by our resistor, which is 470 ohm. Yeah, that's about 52 milliamps of current in the output stage, roughly. I mean, there's also going to be a little bit of residual current draw there for the rest of the circuitry. But that would be a little bit high, in my opinion. I'd be probably looking more to have a current draw of around about 25 milliamps, thereabouts. So to get that, we multiply that. So it'd be 0.025 multiplied by the resistance should give us our voltage. We need 11.75 roughly as a voltage on that multimeter. So I'm going to turn it down. Yeah. And in actual fact, it is actually remaining fairly stable, I must admit. So, yeah. Also, if I was to touch the the VBE multiplier transistor, we'll see the voltage drops. If I take my finger off of it, the voltage climbs back up. I might make that 1K resistor there at 2K2, and I wish I had a 5K pot, but I don't. I need roughly between 2K and 5K there for it to work balanced effectively. But as a VBE multiplier, it is working, so yeah, it's just a bit finicky. As soon as I touch the pot, yeah, all hell breaks loose. And it won't stay stable. So, I forgot what value of pot that was now, 1K. Okay, I made the VBE multiplier a little bit more stable. I'm using a 10k resistor from the base to the collector junction and a 20k linear variable pot there. Using one of these type of pots is very finicky to get what your voltage measurement that you're trying to aim for. I'm still aiming for around about 11 millivolts on my, 11 volts on my multimeter. Now the final design will be 4K7 versus a 10K multi-turn pot, just so that it can be adjusted precisely. But if I slowly increase my pot, we're up to 10, 13, 14, overshot it, 12, 11. I'm going to say that's about right there, 11.5, close enough. As I say, a multi-turn would be better. I'm just touching the VBE multiplier. You can see the voltage is dropping, which is exactly how it's supposed to work, so it's lowering the current to the output stage. If I now take my finger off of it, it should start to slowly climb back up again, which it is. We're now at 9.4, it may take a while to stabilise, but it's getting back up there. And I couldn't figure out why nothing was adjusting. I changed the pot and nothing was adjusting. Turns out that one of the driver wires from the driver transistor to the power transistor came off the board, and so the whole PNP side of the circuit wasn't really doing anything. Anyway, we're now at about a quiescent current now of 10.9 volt, which is the equivalent of around about 23.5 milliamps, somewhere around there. I'm going to make sure that everything is still working and it's still functioning as an amplifier by connecting it back up to the oscilloscope. So I'm going to take that one to put the load on. I need to connect the DDS to the input wire. And I also need to remove this resistor out of series with the supply line so it's not adding distortion. And I'll just turn the thing back on. And there we go. Got a nice sinusoidal waveform going there. It's not showing any signs of crossover distortion or any of that weird clipping that was going on the bottom here. I cured that just by pushing some of these long wires closer to the breadboard there. As I said, breadboard does not make a good layout for a power amplifier. Keep that in mind. However, that's all the modifications I'm going to do to it. I did take the 1 microfarad capacitor I had across the base and the emitter and the collector junctions on this VBE multiplier here. Didn't really see the need for it. So that's the modifications done. So what we might do is I might hook it up to a speaker now and just do a sound test. But before I do that, I want to know what our idle DC offset is with no input signal and no load. So let me just set that up real quick. Okay, with the multimeter in the voltage scale across the output of the amplifier now, no input. I'll turn the load on. And we've got, well, that's interesting to have 1.1 volt DC on the output. That's unloaded. That shouldn't be that high. We've got an extremely high DC offset for some reason. Well, I don't really want to risk my desktop speaker in case it blows it. It shouldn't do, but there shouldn't be a volt sitting there. But we'll turn it on. Doesn't seem to hurt it. Okay, that output voltage of 1 volt there, or minus 1 volt DC offset, is kind of concerning, but the amplifier is quite noisy. I mean, I can put my ear up to the speaker and I can hear it hissing, so it's probably most likely the layout of the circuit on here, and it's just picking up noise, which is why we're getting such a large, well, in my opinion, such a large voltage on the output that shouldn't be there. But it's turned on, it's not doing any damage to the speaker, so we'll take a sound test here. it is working, albeit there is a little bit of noise there and a high DC offset. But again, there could be layout issues here because there's wires going everywhere, so to be picking up noise in every direction possible. But anyway, we're going to end this video here by looking at the final revised schematic to all the changes now that I've made. And here's our finalised schematic. I had to draw it up. Basically the changes are, we've got a constant current source up here for both the long tail pair and for the driver VAS section. We've also got a VBE multiplier in here to adjust our current in our output stage to a roughly 25 milliamps. And it's all seems to be functioning fine apart from that large DC offset. So we've gotten rid of the bootstrap circuit, and even though it was wired incorrectly on the breadboard, but it was actually wired correctly on the schematic. I made a mistake. How that affect the performance, I don't know, but it's in either configuration it's still producing the same amount of output, which is around 25 watts average and about 44 peak, which is okay for the choice of output transistors we've got here. There's not much more else to say about this. The drivers were changed to BD139 and BD140. This this VBE multiplier must now be in contact with these drivers. So in the final PCB design, they'd all be mounted in a line, in the same line on the PCB. They don't have to necessarily be mounted to the heatsink because they're not actually producing any heat. But we could just put a little bar of aluminium across all three transistors with isolators and to join them up thermally. Really it's neither here nor there if it's connected to a metal bar, a separate little heatsink, or to the main heatsink. But normally the drivers don't need to be connected to the heatsink. That's about it for this little presentation. In the next video I will do a PCB, and would having a current mirror in here reduce our DC offset? Probably not. Anyway, I'm the Astro 30. If you enjoyed this video, please remember to rate, comment and subscribe below, and you can always follow me on Facebook and Twitter. The links are in the description as usual. Anyway, this is the Astro 30 saying see ya, have a great day.